move forward. Now we are going to do multiplication. The main thing about multiplication is to realize that it is very simple, right? In binary. Multiplication is very complicated when we are the elementary school student, right? You need to memorize many stuff. For binary, it's very important. Basically, there's nothing called multiplication. It's just addition, but it is what? Addition and operation and shift. Then that can do multiplication, right? Let's do an example. 1011 multiplied by 11, right? This is binary multiplication. What do you do, right? You may have different way, but because we want to match the algorithm, I will start with the least significant bit. I see this is 1, right? So what do? Just copy 101. This is an AND operation, right? If I call this X, this is Y. This is basically just X and 1. Okay. Then I do the other things. Then I see this bit Y, this here, right? What do? I again do the copy. This is what? Y and 1, not Y, sorry. X, again, is X and 1, and then shift. Do you see that? So the first step about multiplication is nothing but just an operation and the shift operation. If this is 0, then I just end 0, everything is 0, right? Then what do? We do addition, right? 1, 0, carry out, carry, right? Then you get this number, right? So if here I have n bits, here I have n bits, how many bits do I have here?
M plus N.
N plus N. Good. We can see this from another perspective. X is what? Equal to 1011. In decimal, it just means that this X is just 1 or 0. Right? I think you all know this, but let's be very careful. This is X0, X1, X2, X3. Basically, it's saying that X equals to X0 times 2 to the power 0 plus X1 times 2 to the power 1, X2 to the power 2, X3 to the power 3. That is what this is talking about. Okay, so for any number in binary, I can represent it as this. So same for the Y, right? So Z equal to X times Y, you just multiply in. It is what? This one times this one. So you have Xi, Yj, 2 becomes 2i plus j. Summation, you keep it. And you see that you do have n plus n bits. Okay. How many cycle of operation do I have to do this addition? How many addition do I need? Let's don't do. You can say what I'm talking about is cycle here, but let's just talk about cycle and addition. How many addition do I need in this case? For example, I have this computation, I only add it once, right? What if I have more bits? Then I need to add more. So how many pairs do I have?
N.
Say again.
I think it's N.
N? Almost. But what is N here? What do you call N? Is it 1 or 2?
2.
2, right? But how many addition do you do? How many addition?
1.
1, right? So is it N? What do you want to modify your answer a little bit?
It's n minus 1.
Yeah, thank you. Right. Although this is trivial to you, but once you go through, you know why, right? Because I do have n number to add, but I only need to add it n minus 1 time. Okay. You may feel that why I want to take this, right? Indeed, n and n minus 1 is not a big difference, but you need to know the exact number, because when you do the hardware, you know that you only need n minus 1. Otherwise, you will get lost when you're designing the hardware. So to do multiplication, now you understand it is easy. It is just addition. I mean, first n and then shift and then addition. How do you do shift? Well, you don't need to do shift. You just wire it. You just wire into the next level, right? So basically, there's no shift operation. We lay it out so that it's just like what we are doing here. Here in particular, m equal to 4, n equal to 4. So how do we do this? You see that here I have x0, x1, x2, x3. I shift them already, right? So I need the wire to wire them so they will shift to here. It's not good in terms of layout, but let's do that. Let's say, assume we don't care about the layout and the layout effect on delay so much. How about for y? Look at this. Y is coming in this way, is horizontally, right? X is vertically, right? So I say we do n. Look at this. First, y0 and all of them. I have an AND gate. Do you see that? So this one and all of them. Then I also have this 9. I have y1, which is this one, and all of them, right? And then y2 and all of them, y3 and all of them. So what this AND gate are doing is basically write down this 9, right? Maybe I don't need to show here. Just write down this. These are what the AND gate are going. So you do have 1, 2, 3, 4. You have n rows of AND gate. However, in terms of addition, I have 4 number. I only need to do 3 additions, right? So each of them is an adder. Here is ripple carry adder, right? So what does it do? First of all, this one, we know that no matter, this is just n, right? So you just copy, right? So we don't need to do any addition. This one come out as Z0. And this one, once you do the n, I'm going to add to the next one. So that's why we shift it. This one will go to this half adder because this one doesn't have carry in for sure. So I use half adder to save it. Then you may have a carry out, right? And then up to here is more complicated. I need to add this one and this one. And then this one might have the carry in. So that's why I have this one. And then I need to go one more step to here. This one, right? 1 and 2 is talking about this adding, right? So everything looks very normal. And your output will be C0, C1, C2, all the way to C7. Again, this is n plus n, in this case, equal to 8, right? From 0 to 7, you have 8 bit. So this is the simplest n bit adder. The easiest one, right? It's like what we do for multiplication. Any questions? Now, if this is easy, then we need to again ask ourselves, what is the critical path, right? So again, this is a 4x4. It's a 4x4. I think I have typo. This should be 4x4 multiplier, right? But why I only have 3 rows of adder? That's what I just trick you. I say you say n. I say it should be n minus 1. You know very well, right? Here I copy what it is, because you only need to add 4 numbers, so you only need 3 rows of adder, right? So I think you're okay with this. Now, what is the critical path? You will see that they're pretty similar. So here we just pick up this path 2. Okay. What do we see? From left to right, basically it is carry, t carry from here to here. Okay, from top to bottom, this is t sum. Okay, and do not forget we also have the AND gate, right? So for every signal, we start with this AND gate. This is the AND, right? And then how many do we need in order to propagate from left to right? But again, we say that this one has, because we have n plus n bit, right? Correct? We have n plus n bit. So it means that I have n plus, how do I say? We are doing n bits times n bits, right? So the depth here how much propagation do I need from the top to bottom? It's going to be n minus 2 t carry, right? Because you have n bits and I only have n minus 1 row. So it's going to be n minus 2 t carry, right? So if you look at here, this is 1 t carry, this is another t carry, right? So here you actually have n minus 2 t carry. So here is n minus 2 t carry. Okay. But how about for going laterally? Here you have m, right? You have m divides, right? So this is going to be m minus 1 t carry, right? Because you have m adder. So over here, you have m minus 1 t carry. Okay, and that's why if you do n minus 1 plus n minus 2, then you have this amount of t carry. Any questions? And then, actually, I'm a little bit lost. I don't know why I put this n minus 1 t sum. Let's see. So anyone can help me? What did I do wrong here, right? So I give the t carry right, but then we have this t sum. Okay, yeah, I say something wrong. I'm sorry for that, right? So first of all, let's do the path, right? This path, you go from here to here. You go from here to here. right? So at the same time, then later you will also go down. This path are the same. Okay, so in terms of T carry, right? Although I put here, but this carry is just the same as this one is the same. Maybe I should not do this. But these two carry, they happen at the same time as these two. Right? So here I also have T carry. This is M minus 1, N minus 2 T carry. Okay, because I need to go laterally and then propagate downward and then laterally. So this is the 2 T carry. I cannot just say this because this one is not the critical path. I say the wrong thing. I'm sorry, right? And then going down, you also have N minus 2 plus 1. This N minus 2 is this one, right? N minus 2 T sum. But then later plus 1 is this one need to go out, another T sum. Right? So that's why I put N minus 2 plus 1 T sum. So that's why you have this, right? I confused you. Can you let me know if you still don't understand? So I can clarify. Okay, so let me summarize one more time, right? So the critical path is from here to here, right? I cannot just do this one. This is not the right one. This is faster than the critical path because this one need to wait for all this data, right? So going right, these are all T carry. Of course, this will be N minus 1 because I have N bits. And here you see that it will be N minus 2 because the overlap, we don't care, right? And then again, you minus 1 because you only propagate in between. So N minus 2 plus N minus 1 T carry. But you also need to go down. Each of them is T sum. That will be go to N minus 2 T sum, right? But however, we also need to find the last one, the last output. This one is another T sum. So that's why it's N minus 2 plus 1 T sum. Okay, so this is the critical path of a multiplier. And you do see that you need to optimize both the T sum and T carry in this case. So, okay. So let's say it is okay. Then we say it is too slow, right? Because I have a lot of T carry and T sum. And this is what we said before. So now we say, hey, can we do something? We do something called carry save multiplier. We don't do the propagate the critical, the carry. For example, here I need to wait for your carry in order to operate. Wait for your carry in order to operate. You see here, we directly put the carry to next stage instead of the same stage, right? So this will operate together, right? So let's look at the critical path. The critical path will be something like this. You come in, right, and then go here, and then go here. Now, very special. I just told you that you only have 3 rows, right? Because you have N minus 1 row of adder. Here in this carry save, you need to add something called vector merging adder. This one, you can use a very fast adder to compensate for it. You have 1 extra stage, but if you can make this very fast, then you actually save a lot of time. Let's see why, right? So what is the worst case delay? This one, first, of course, you have the LAN gate, right? What we call is TLAN. Let me just do it in this way, right? You need to do the LAN gates. That is okay, right? And then after that, you have 1 carry, 2 carry, 3 carry, right? You only have N minus 1 T carry. It depends on the depth, right? You are doing M bits times N bits, right? So you have N minus 1 T carry. Then you reach here already. The problem is here you have not finished your computation. Then you fit everything into the vector merge adder, just a special adder. For example, carry look ahead that run very fast. Assume you can do that. Okay, so this becomes T merge. This is the critical the time, right? Compared to this, you see that as long as your T merge is less than n minus 1 T sum and plus n minus 1 T carry, you gain the speed. Is that clear? Any questions? Right, so basically it is just saying that because carry is giving us trouble, let's do not add it on the same stage. And because I don't add it in the same stage, I no need to wait for it to propagate across this stage, right? I save the n minus 1 propagation, right? Remember, we need to do this propagation. Now I only need to have this n minus 1 propagation. It was like n minus 2, but then I have extra stage. I have n minus 1, right? And then eventually we group them together and do an addition. Assume you can do a very fast addition using the vector merging adder. Okay, this is called carry save, right? So carry save is very useful because we can lay out it very neatly. Remember, I say the shifting, actually, we don't implement it, we just lay it out, but you see that it is like this. How are you going to lay out? It is going to be very messy, okay? But for carry save multiplier, what we can do is, because our carry is fit to the next stage, so we can just lay out them in an array very nicely, right? And then when the XY come in, the Y0 coming here, it just LAN gate. Here it does all the LAN action, right? This group and this group is just do the LAN and then it come out just like here, right? And then we start doing the carry save to the next stage. I mean, carry to the next stage and then sum. So it, maybe I should flip it horizontally. Then you will see that, of course, then they are the same, but the point is not horizontally actually, right? So here although we say this is Y0, right? But it is the same. I just call this, I just go from the left, right? So you see that X0 and Y0 here, it gives you the Z0, right? And then you go to the adder and then you give you the Z1. Right, so here is Z1, like what I'm showing here. This is X1, Y0, X0, Y1 becomes Z1, right? So here X0, Y1, Y0, this one gives you Z1. Okay, is this okay? Any questions? Okay, so this one is a very important invention, right? But how do you do this vector merging adder, right? You can use a carry look ahead, right? Or you can use something called tree multiplier. And I was want to spend some time to go over this. How do you do this? Now, if you look at the left, usually when you do this partial, these are called the partial products, right? You do addition. How many adder do you need for this addition, by the way? How many rows of adder? I have 4 numbers. These are 4 numbers that I need to add, right? This is like this. Like this one. I want to add all this number. Okay. I should give you, right? For example, I might be adding 1 0 1 0 1 1 1 1 0 1 0 1 1 0 1 0. That is what we're showing, right? So you need 3 adders, right? 3 rows. Okay. So now Wallace tree is that it helps you to build a multiplier by simplifying the adder. Okay, so what does it do? First of all, we reposition it, right? Organize it into a tree shape. It really doesn't matter how you put it, right? So you have this one go up, go up, go up, right? Then it becomes this. Is that okay? It becomes a triangle. Then the next thing, we try to optimize it. First of all, we say if I have a half adder, I can reduce this one into 2 points. One is that you stay here, you can have a sum, and then you may carry over, right? So if I use this adder, then this may becomes this. This 2 points, or maybe I should say this one, right? It becomes this point after addition. But at the same time, it will carry ahead, right? It's going to carry something forward. If I do an adder, right? So for example, let's say this is 1, this is 1, then this one becomes 0, this becomes 1. Is this okay? And for this 2 point, I also can say that I make a half adder. Half adder only have 2 input, A plus B, right? If this is 1, this is 1, then what happens? It becomes the sum, right? And then carry over. Right? So by doing this, my tree becomes more uniform. So I try to make a uniform row, right? After this, I continue to reduce the tree. This time, what do I do? I group this as a half adder, this 2 point, right? If this was 1, this was 1, then what happened? This one becomes 0, becomes 1. And then I carry over. Is this okay? But here, I use a full adder, so I have 3 points, right? So when this 3 points add together, I'm running out of color. For example, this 3 points, right? Let's say this is 1, and then plus 0. So this becomes what? 0, and then 1. I carry over 1, right? So this is basically telling a way to reduce a complex tree into more uniform one. But in this process, it tells me that I can use a full adder for this 2 bit. I mean, half adder for this 2 bit, half adder for this, full adder for this. And then eventually, I will just use something very fast to calculate them. Because now it's only addition of finally, addition of 2 numbers, right? Again, I can use the so-called vector merge adder. And the speed is going to be very fast, log n base 32. Okay, so it's a very fast adder. Think about here, what was the speed for the regular adder? It's in the order of n or even 2n, right? So if you have 128 bit, right, you may have 256 units of time. But now you use this log, although it is log 3/2, I don't know exact number, but it may be just 10 units or 5 units of time. Okay, is that okay? Is that clear for what I'm drawing? What I'm trying to say? Basically, you have this number you to add, and this tree algorithm help you to find out how to minimize the number of adder to add. What do? We first just whatever sticking out, get rid of them, right? So we get rid of them. Here we use the half adder. Then this becomes one, and one result here and then another result here. Here we also use half, that's why you got 3, right? Because it propagate, carry 1 here, and then you have 1 here, and then another propagate, there's a 3, 3, 3, right? And then you continue this to make it 2 plus 2 addition. Any questions? Let me pause for half minutes to see if you have any questions. Now, if no, then let's just go to the how we implement it. We already have all this thing, right? So let me just remind you, this is x1, right? x3, x2, x1, x0. And from here, it is y0, y1, y3, y4, right? You do this AND operation, right? So for example, for this one is talking about what? The 3, right? Talking about this 2 point. And this 2 point is what? x3, y3. And this is x3, not x3. This is x1, right? This is x1, y3. This is x0, y4, right? This point, right? This number is x0 times y4 and y4. This is x1, right? And y3, right? And then this is saying that we want to do half adder, right? With x0, y4, x1, y3, right? So this is exactly what we are doing. x0, y, no y4, y3, I should call it y3, 1, 2, 3. This is the wrong label, right? 0, 1, 2, 3. x0, y3, x1, y2. I gave you the wrong number. Is that okay? Right, because this is actually 2, not 3. This is 4, right? So if you look at the graph, here, this is what we're doing. x0, y3, xy1, 2, we go through this half adder, right? So whatever number come in, we do the addition. And similarly, these are the adder that we use for the first 1, 2, 3. And then later we combine them together, becomes the full adder, 1, 2, 3. And then we have a final adder. Hopefully this is very fast, right? So here, right, how many adder do we use? We use 3 full adder and then 3 half adder, okay? But if you refer to carry safe is the one that is simple. It also have it also have this final adder. How many full adder do we need? Carry safe. We need 1, 2, 3, 4, 5, 6 full adder. 1, 2, 3, 4, 5, 6 half adder, right? Carry safe needs 6 full adder and then 6 half adder. So that save a lot of area, and also the speed will be much faster, right? The only problem for this is irregular, right? Compared to carry safe, right? Because you really don't know. I mean, this is a second stage has much more adder than the first stage. Okay, I think that's I have for this class. Then I will talk about the midterm 2 and also the project. Any questions? No? Okay, if no, then let me talk about midterm 2.